All right, ladies and gents. So today's topic is going over covalent bonds and how they're formed. The first thing I want you to remember is the purpose of bonding, which is to reduce potential energy of atoms, because atoms have a lower energy when they are together in compounds with a more stable electron configuration. Now, a lot of chemical compounds are molecules, and there's going to be a very specific implication of the word molecule. A molecule implies a covalent bond, okay? So from now on, every time you hear the word molecule or molecular, then the first thing you need to think of is covalent bond. Now, a molecule is an individual unit which is capable of existing on its own, which you might think sounds kind of common sense, but it's not, because ionic compounds are completely different. Excuse me. So a molecule can consist of two or more atoms of the same element. For example, oxygen, ozone, hydrogen gas, nitrogen gas, things like that. Or of course, you can have two or more different atoms, like we've got water, sugar, glucose, H6, examples like that. So a molecular compound is a chemical compound whose simplest units are molecules. So here's an example of 3 different molecules. Each of them are going to be held together using covalent bonds. So if you have, hold on a sec, just came in. Of course, I'm opening all the wrong applications. Right, so if you have a molecule that has 2 different elements, or 2 or more different elements in it, rather, like you have either water, which has only 2 elements, or sucrose, which has 3, these are molecules of compounds. Sorry about the terrible handwriting. And this one, oxygen, where they're all the same, that's a molecule of an element. Okay, element because there's only one type of atom present in the molecule. And of course, compound is where you have more than one type of, oh shoot, sorry, that's my phone. Hold on. Freaking Mondays. Okay, so molecules of elements, molecules of compounds. Next, how is a covalent bond formed? Well, like I said, bonded atoms have a lower potential energy than unbonded atoms, and it all has to do with the distance between the atoms. So at a large distance, atoms don't influence each other. So we set the potential energy at 0. Ooh, stairs. Get the book out. All right. Yeah, so if you have your book or not, it's up to you. I'm on page 169 with the graph that's there, where you can just look at it on the screen. So, okay, so when they're far apart, we're going to go kind of counterintuitive, which is right from like right to left. As we go, we have, what am I saying? As the atoms are far apart here, as they get closer together, you can see that their potential energy decreases. Okay, so you've got potential energy in kilojoules per mole on the y-axis, and on the x-axis, the distance, and they're using hydrogen as an example. So here you can see the potential energy is set at 0 when they don't influence each other. But as they get closer together, you see what happens to the potential energy. It decreases greatly until you reach the lowest potential energy. This is where the bond is formed. Now, the distance here, 75 picometers, that is the bond, what's called the bond length, which I'll talk about a bit later. And then you can see here, the potential energy is minus 436. Now, what happens as you go, why it increases here is because when you have the atoms are too close together, you start getting repulsion from the electrons, okay? So as the atoms are far apart, they start getting closer together. You start getting attraction from the electrons of this atom to the nucleus of that atom and vice versa. So electrons here attracted to the nucleus here. And then at the bottom of the curve, that's where the bond is formed. If you move them closer together, then you start getting repulsion, both from electrons of each atoms and also the nuclei as well. So looking at hydrogen as the easiest example, because then you can just deal with one proton and one electron. So we have a nucleus of one proton surrounded by one electron. And so these subatomic particles are going to start to interact as they get nearer to each other. So here we have a diagram of the attractive and repulsive forces. The nucleus of one atom is attracted to the electron cloud of the other atom and vice versa. But you also have this electron cloud, which repels this electron cloud, and this nucleus, which repels this nucleus. So there's a very narrow window where you have all of those repulsive forces at a minimum and the attractive forces at a maximum. And that's where the bond is formed. So the attractive forces, which you see here in red, those decrease potential energy. But the repulsive forces that you see in blue are going to increase potential energy. So again, the amount of attraction and repulsion depends on how close they are to each other. When they first see each other, which by see, I would mean as soon as the electrostatic forces come into play, meaning the electron-proton attraction or the electron-electron or proton-proton repulsion. That as soon as those charges started to interact, that's when they quote unquote see each other. So electron-proton is stronger than the repulsions. So the atoms are decreasing in potential energy, which is what you see on the graph. That attractive force dominates until a distance is reached where the repulsion equals the attraction. And this is the valley of the curve here, where the two opposite forces are equal. But like I said before, if you push the atoms closer together, the potential energy increases greatly because then you have the repulsive forces, which are then going to overtake the attractive forces. Now, when atoms are bonded, they can still vibrate a bit. And as long as the energy stays close to a minimum, they will stay covalently bonded. So as I pointed out before, for the hydrogen atoms, the hydrogen molecule, you could see, do I have the graph here? Yeah, not the graph, but remember how I said that you measure radius, which is where you would measure the distance between the nuclei and then cut it in two, and that's the radius of your atom. But we have here the bond length. So imagine there's an invisible attractive force holding the two atoms together. And that bond length represents the distance where the potential energy of the atoms is the lowest. And every single covalent bond is going to have a characteristic bond length because of the size of the atoms and like the number of valence electrons and things like that. Here we go. So that's the bond, that's the bond length here. Okay, which represents the distance. So in order to form a covalent bond, the hydrogen atoms need to release energy, and it makes sense because as individual atoms, they have a higher potential energy than when they're bonded. So how do you go to a lower energy? You have to release that energy. The amount of energy that's released equals the difference between the potential energy at a zero level, which is separate atoms, and the bottom of that curve where the atoms bond together. Now, if the two atoms release a particular amount of energy when they bond, let's go back to here. So these atoms release a total of 436 kilojoules of energy per mole of atoms. Remember, I told you before, probably not, but I'll remind you again. When energy is released in an exothermic reaction, it's represented by a negative number, which seems kind of opposite of logic. You'd think if it's being released, it would be positive, but no. When energy is released, it is a negative number. So here you've got a hydrogen molecule. If the hydrogen atoms release 436 kilojoules of energy when they form the bond, in order to break the bond, you're going to have to add at least 436 kilojoules of energy per mole. And that is a second characteristic of covalent bonds. That's called bond energy, the energy required to break a chemical bond and form neutral isolated atoms. Freaking Monday. Okay, so a couple things you can remember, because it's always true. Bond formation is always exothermic. Heat is always released. And bond breaking is always endothermic. It requires energy to be absorbed. So if you look at a chemical equation, let's say the formation of water. Okay, it's not balanced. We're not going to do that for a couple chapters yet. But you've got a hydrogen molecule and an oxygen molecule. In order to break those bonds, you have to input energy. But when water is formed, it releases energy. Now, whether or not the reaction is exothermic or endothermic overall depends on how much energy goes in and how much energy comes out. If more energy goes into breaking these bonds than energy is released, overall, the reaction is going to be endothermic. If more energy is released than what is put in, it's exothermic. But every single chemical reaction has both an endothermic and an exothermic part, I guess. Right, the unit of bond energy, kilojoules per mole, and this basically gives you an idea of the strength of the bond, meaning the more energy it requires to break the bond, the stronger the bond is, which should make sense. So if the hydrogen atoms release 436 kilojoules per mole, then of course, in order to break up the hydrogen molecule, you're going to need to put in at least 436 kilojoules per mole. If you give it 430 kilojoules, nothing's gonna happen. And again, both of these characteristics are unique for every single molecule. So if you change the atoms, you're going to change the way that the atoms interact. You're going to change the bond length and the bond energy. So it's very specific for the kind of molecule. So here's just a table to give you some ideas. So for some reason here it's 74, not 75, but it doesn't matter. So for hydrogen bond, it is 74 or 75 picometers and the energy is 436. If you compare that to fluorine, which is another diatomic molecule, you can see that the bond length is like roughly twice as long, which means the fluorine atoms are further apart and the bond energy is much lower. And it makes sense because these guys have a lot more electrons than hydrogen does. So it makes sense that they would be further apart. And then you look at chlorine, it's even further, but the bond energy is higher than fluorine. So these two have a stronger bond than F2 does. So just some examples of bond length and bond energy. It's different for every molecule. Now, let's look at why it makes, for the hydrogen example, why it makes it stable. If you look at the electron configuration, an individual hydrogen atom has a single unpaired electron in its 1s orbital. Good Lord, I have an issue today. So they each have one electron and one s. So we got that one. And again, this is one of the few times that you use orbital notation because it's just easier to see. So when they form a bond, they will share 2 electrons in the 1s orbital, which gives them the configuration of helium. Okay, and that's what makes them stable. So you have to look at how electrons are shared. For example, carbon's another good example. So carbon is 1s, 2, 2s, 2, 2p2. Now the interesting thing about carbon, and I don't know if I talk about it. Do I talk about hybrids now? Ooh, with Octet Rule. Oof, yeah, okay. Sorry, I'm just looking for when I'm supposed to talk about hybridization. Oof. All right, I'm just going to talk about it now because it's important. All right. For carbon is an interesting example because all 4 of these electrons are valence electrons. Because remember, valence electrons are in the highest energy level, the outermost shell, and both of these are level 2. The problem is that 2p and 2s don't have exactly the same energies, right? Otherwise, they'd be the same orbital. So how is carbon going to have 4, oops, just violated Hund's rule, find 4 electrons to share in the 2p orbital when 2s is already full? It's just kind of all kinds of complicated. So what carbon's going to do is it's going to combine all 4 of these orbitals. Again, 1s doesn't count because that's inner shell. And you're going to end up with something like this. So you get 1s, and then you're going to have 1, 2, 3, 4. And all 4 of those are going to go in, and you're going to form something called an Sp3 hybrid. So this is called a hybrid orbital. It's called Sp3 because we're combining the 2s and we're combining all 3 of the 2p subshells or sublevels. So that's why it's called Sp3. Now carbon has 4 electrons, all of equal energy, and 1 in each separate orbital. This way it can share that electron with, say, a hydrogen. So there's a 1s here, like 4 hydrogens, if you know what I mean. Okay, that's getting in the way, but anyway, so that you'll have a hydrogen for each one and it'll share. You also have sp2 hybrids and sp hybrids. I think I'll talk about those a bit later. Okay, so you can see here, that's what gives hydrogen a stable configuration, because now it looks like they each kind of share helium. Now, besides hydrogen, and I think up to past boron, atoms follow what's called the octet rule, because except for the first energy level, all of the other energy levels hold a maximum of 8. That's why it's called the octet rule. So this is chemical compounds tend to form so that each atom, by gaining, losing, or sharing electrons, has an octet of electrons in its highest occupied energy level. And you can think back to when we looked at electron configuration. The reason why it's always 8 is because even if you're in period 4, periodic table. Even if you're in period 4, you've got 4s, 4p, but this is 3d. So this is not in the same energy level. So the maximum number of electrons in the outermost shell is going to be the 2 in s and the 6 in p. That's why it's always 8. Again, except for period 1. So let's look at fluorine. Fluorine atoms bond to form a fluorine gas, F2. Each fluorine has 7 electrons in its highest energy level. So they're going to end up sharing the last one with each other so that they each have a total of 8 electrons. Here's another example of HCl. So you've got hydrogen with its 1s electron. It's going to share with the chlorine's last 3p electron. And so hydrogen is going to have the configuration of helium with the 1s2, and chlorine is going to have, I think it's argon. Yeah, the 3p6. Again, a total of 8 because they're sharing. Now, of course, there's exceptions like everything else. Most of the main group elements, like I said, are going to follow the octet rule. Hydrogen obviously can't because it only has, each hydrogen has only 1 electron, so there's no way it can get to 8. Boron is another example of an exception because it only has 3 valence electrons. You're never going to see an example of an atom that shares 3 electrons and in exchange it gets 5. It doesn't work that way. Thankfully, the universe is quite fair. So if boron has a maximum of 3 electrons to share, so it's got 2 in the 2s orbital and 1 in the 2p orbital, it's only going to share 3. So it's going to have a maximum of 6 in its outer shell, even when it's bonded. So it will not form, it will not follow, sorry, the octet rule. Sometimes you can have, I forget what it's called, hyper something or other, hypervalency, I think, when you can have an atom surrounded by more than 8 electrons. And we'll see that when we start doing Lewis structures, which, yeah, I got time for. All right, so first thing is electron dot notation. I don't really know where this is extremely useful because we don't usually do electron dots for individual atoms, but basically what it means is that you're using dots to represent valence electrons around an atom. Now, the way that you're supposed to draw them, you draw them around the chemical symbol, but you're supposed to start 1 on each side first before you pair them up, just like following Hund's rule when we do electrons in orbitals with more than 1 subshell, like the p, f, and d orbitals. You do like up, 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 and down, 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 like that. Same thing here. Although, like I said, it doesn't really matter too much, but this is called electron dot notation. We do not represent inner shell electrons because they belong to that fluorine atom by itself. They're not going to be involved in bonding. So these are just some examples of how you would draw them. It doesn't really matter what side you put them on. So Mg, you could have 1 on top, 1 on bottom. I don't think it really matters. Okay, I don't really care about this because it's not important. Blah, blah, blah. All right. So the main idea for today is Lewis structures. Lewis structures are basically kind of using electron dot notations in order to show the structural formula. Now, we've seen molecular formulas like H2O, but we haven't seen structural formulas to actually show you how the atoms are arranged. And so the way that you do this, you can use 2 dots like that. So for example, if you do electron dot for that hydrogen, it's got 1 electron, and then that one has a 2nd electron. When you put them together, you do like that. But in a Lewis structure, you're going to end up replacing the double dots with a line to show a single bond. So I'm going to go ahead and just skip to how to do it because it's just easier if I explain how to do it. Okay, so like I said, when you have a pair of electrons that are being shared in a covalent bond, you're going to use a long dash. And then you're going to have what are called lone pairs, which are electrons that belong just to that atom. Okay, right. So here's examples of structural formulas. All right, let's get to the procedure. All right, so there is a procedure for drawing Lewis structures, and it's pretty simple. So if I ask you to draw a Lewis structure for iodomethane, which is CH3I, first thing you're going to do is you have to draw the skeletal structure of what the molecule is going to look like. If carbon is in the formula, it's going to take center stage. It's going to be in the middle of the molecule. If carbon is not present, it will be the most electronegative element. So I would do that first. I don't know why I didn't have that there. Okay, so first thing we do, we've got C, we've got 3 H's and an I. So the first thing I'm going to do is I'm going to draw a C, and it doesn't matter which side you put them on. You can have I on the top, left, right, whatever. I just chose to do it this way. Once you've done this and you figured out where the atoms are kind of going to go, you're going to count all of the valence electrons in each atom that's going to be combined. This is super important, like the most important part. You want to get the number of valence electrons right. So you consult your periodic table. You see that carbon is in group 14, so it has 4 valence electrons. Each hydrogen has 1, that's a total of 3. Iodine is in group 17, so it has 7 valence electrons. You're going to add those up. So you have 14 electrons to distribute over this molecule. Is everybody with me so far? I hope. I'm trying to like just get to like the, what do you call it? Like get to the point, I guess, and not like kind of beat around, whatever. So I have carbon, carbon goes in the middle. I've counted the valence electrons in each of the elements that are present. I know that I have 14 electrons to distribute. Now I'm going to fill in my bonds, and I'm going to start by drawing a long dash between all of the atoms to represent a single bond. And now remember, each long dash represents a pair of electrons. So as I draw the lines, I'm going to count how many electrons I have used of my 14. So here's 2, 4, 6, 8. So I'm down to 6 electrons. I have used 8 and I have 6 left. And the last thing that you're going to do is you're going to fill in all of the lone pairs of electrons that belong to individual atoms following the octet rule. Following the rule that all atoms, except for the exceptions, yeah, besides the exceptions, they're going to follow the octet rule. Now, hydrogen is an exception because it has only 1 electron to share. So it is not going to have an octet. I don't ever want to see any of you drawing dots around hydrogen. Nuh-uh. No way, no how. Carbon, if you count your lines, already has 2, 4, 6, 8 electrons around it. It already has an octet. So that means I'm going to fill in the octet for iodine using a dot to represent an electron, of course. And now the last thing that I do is I'm going to count my total number of electrons and make sure that I have 14 and only 14. You have to have exactly the correct number of electrons. So I've got 2, 4, 6, 8, 10, 12, 14. Okay, I have used all, let me erase that. I've used all of my electrons. So this is the Lewis structure for iodomethane. And don't worry, we'll be doing tons of these. Okay, let's do ammonia, NH3. Again, there's no carbon here, so hopefully you kind of logically put nitrogen in the middle. Doesn't matter which positions you put hydrogen in. And then you have to count. You got to count the number of electrons, and I have a southern accent all of a sudden. Nitrogen has 5, 1 each for hydrogen, that's 3, so that's a total of 8. Put in my single bonds, that's 2, 4, 6, and then give nitrogen its octet. Remember, hydrogen's an exception that doesn't ever have an octet. So I have fulfilled the octet rule for all of my atoms, and I have met exactly the number of electrons for this molecule. So that means that nitrogen has a lone pair of electrons that does not participate in a bond, but just kind of stays off to the side. And that's going to have a huge impact on the shape of this molecule, but I'll talk about that much later. Okay, hydrogen sulfide, same thing. Put an S. I'll just put one on each side. Hydrogen, that's going to be 2. Sulfur, I don't have a paper periodic table, but I do believe it is underneath oxygen, which means it has 6. Periodic table. Oh, yeah. Yeah, it has 6. So 2 plus 6 is 8. So I've got 2, 4, and then fill the octet, 6, 8. Done. Now I'm going to do a tricky one. What about carbon dioxide? First thing, carbon goes in the middle, oxygen on each side. Carbon has 4, oxygen has 6 times 2, that's 16. Okay? Okay. Fill in my single bonds, that's 2, 4. Put in my octet. I had 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Uh-oh. That don't make no sense, because in order for every single atom to have a full octet, that requires 20 electrons. When this happens, if you fill in your octet and you are using more electrons than what you're allowed to use, that tells you that there is a multiple bond in play. And what I mean is a double bond or a triple bond. And the key is, for every pair of electrons over the number that you have, that represents 1 extra bond. So what I mean is, let's take away 2 electrons. Oh, I don't have an eraser. If I fill in a double bond here, that means carbon now already has an octet, because you've got the single bond on the left, you've got the lone pair on the top, and the double bond on the right. And then that means I got to fill in the octet for that oxygen. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Still 2 too many. I gotta go back far. Okay, so that means, if I start over, that means each of these is a double bond. Now, carbon already has an octet because it's got 2 double bonds. That's a total of 4 bonds. It's 8. Filling in the octet here. Oops. So I've got 2, 4, 6, 8, 10, 12, 14. Oops. Why is there an extra dot there all of a sudden? Bruh. I'm having a day, I tell you. 2, 4, 6, 8, 10, 12, 14, 16. That's it. So again, when we had our first structure like this, that was 20 electrons. And I told you we only had 16. And the key is, for every 2 electrons over, for every pair of electrons over, that is that's another bond in there somewhere. So I am 4 electrons over, which means I need 2 extra bonds. The elements that you're going to see that have a tendency to have multiple bonds, the 3 big ones, carbon, nitrogen, oxygen. Nitrogen in particular loves triple bonds, which is 3. So if you just take N2, for example, just put them next to each other. Each one has 5 electrons, so I have a total of 10. If I do a single bond, that's 2, 4, 6, 8, 10, 12, 14. If I need 14 electrons for this structure, that means I need 2 more bonds, which means I need 1 here and 1 here, which means I erase those. So it's 2, 4, 6, 8, 10.